Hello, everyone. This is Christine Perey, chair of the XaiR for Enterprise Alliance Research Committee, and welcome to the Area Research Committee webinar on the subject of XR and AI. I'm happy to welcome Sruti. She's going to introduce herself in more detail. So welcome, Sruti, and thank you for participating in today's webinar.
Yeah, thank you, Christine. So hi, everyone. My name is Srinidh. I'm a second-year PhD student at Carnegie-Mellon University. I work in electrical computer engineering. I work in that in-between area of XR and AI. With that, I can get into the talk and get into some more details about what I do. So the thing I want to talk about today is, can we use AI, and more specifically large language models, to augment physical intelligence? And I've been looking at this from the lens of a cognitive assistant, so some kind of an assistant that can kind of understand and help a person through doing tasks in the physical world. Like I said, a little bit about me. I'm a PhD student at Carnegie-Mellon University. I'm advised by Professor Anthony Rowe. And my lab generally looks at a whole range of sensing technologies and a lot of and some graphics with the XR and some of the ML side. I'm working in electrical computer engineering, but I do have a background in human-computer interaction as well. So my work kind of lies in that in-between spot of XR, machine learning, and a little bit of usability and that side from the HCI background. So jumping into the talk, all of us interact with physical world devices every day. Like, we make coffee every morning, we sometimes build appliances, we build furniture. Except one of the core problems is that even though we do all of these tasks, the assistants we have for this are primarily text or images. They're 2D information, and they're not aware of the user's world. So they don't actually know what the user is doing. They're just kind of paper instructions. And so there's this little disconnect between what the task the person is doing and what they're seeing on their instruction guides. That said, we've had this vision for a very long time. If you're familiar with Iron Man and Jarvis from the movies, it's probably one of the really great examples of this assistant that's, walking through a person to do their everyday task and looking at what they need and kind of providing that to them in this physical space. And we've kind of worked towards building that over the years. There was this concept of MEMX in 1945, where we had different devices that kind of worked together and tried to get to do a task that was interconnected. We had things like chatbots that slowly started to come out in the 1960s. And then about 10 years ago, we had Siri and Alexa, which was like the first great voice-based assistant that could actually do tasks that you asked it to do. And then now we're seeing these large language models that are great at being virtual assistants. Like, we can type in, send images of what we want, and kind of specify what we're looking for, and it gives us pretty good answers on how to do a certain task. Except that interaction with the physical world directly is still a struggle. So let's start by defining what we think a cognitive assistant for the physical world should be. It's something that should understand the world, something that should be able to reason about the world, and then be able to respond to the world. So in a more technical sense, it's kind of like the sense, plan, act framework that robotics uses, but I kind of changed that to sense, reason, act for our use case. And this becomes more realistic today because, firstly, we have much better sensors and much better abilities to process the sensor streams. So we're able to make sense of what's happening in our space much better. We have much better AI. Even in the last 2-3 years, AI has changed so drastically. And now we have general purpose and multimodal large language models, foundational models that can help us do reasoning on all kinds of data without being super specific or to a use case or to a sensor even. And then we have much better ways of responding to physical world. We have XR devices that are getting more lightweight and easier to use. We're having we have better display technologies and rendering technologies. And so kind of bringing these three together is getting much more realistic. Except that actual combination is hard. All three of them in silos have gotten better, but how do we put them together? They're hard, firstly, because large language models are struggle to understand 3D spaces. They're pretty good at images now. We can do decent with videos, definitely amazing at text, but 3D spaces is still a stretch. The next thing is large language models are still really compute heavy and memory heavy. And even though people are working on distilling that, the actual good accuracy ones are still massive. But on the other hand, we have XR headsets that we're trying to make as lightweight and as small as possible. And so running these large language models on a headset is a challenge. And lastly, LLMs still output primarily text. And so being able to go from that text response and actually generate XR content is still also a challenge. And so to kind of address these, I worked on this paper called XaiR, which is an XR platform that integrates large language models with the physical world. All of our information, our code, everything is open source, so you can also take a look at this project website that has the paper and the code for it. But I'll give you a brief, I'll walk through the general idea here. So in order to address these challenges, the first one being that XR headsets cannot actually run large language models natively, we built a split client-server architecture where we had the headset interact with the physical environment. So it's what captures data and creates XR content, but then all the LLM inferencing happens on a server nearby. So this allows the headset to stay lightweight and do all the things it's good at, which is physical I/O, and not worry about the inference. The second part is LLMs struggle to understand 3D environments. And so what we did is we took advantage of the camera and microphone sensors on the headset, and we captured the world in the format of images and audio. We then send this over to a server where we have a reality encoder, as we call it, which processes this information. So it takes your frames and it does some frame selection to pick the most relevant frames. It does speech to text conversion and basically puts all of this into a format, into a prompt that's understood by large language models that we have today. We can then send this to these large language models. We use multimodal ones that can do text and images. And then that gives you some response, which goes back to the headset. Headset creates XR content. Now, the other thing that we noticed is that, well, different LLMs are trained for different purposes. So different ones give us different responses. And if we want to be able to get text feedback and, as you can see, arrows that are actually pointing at specific objects, we want to be able to get different kinds of information from different LLMs and use the fact that each one is good at different things. And so in our specific use case, we actually built a system that allows you to have multiple parallel LLMs that can run, which is only really restricted by what your server can hold. In our specific use case, we use GPT-4 Vision, which was the Vision LLM at the time. And then we use Ferret, which is one of Apple's large language models. And Ferret's really good at giving us 2D bounding boxes in your image. So you can give it a text prompt and it identify the locations of different objects that are relevant. And then GPT-4 Vision, as most people probably know by now, is probably still one of the best models that can reason about images. And so what we did is, so we use both of them to get our responses. The next problem we tried to solve is the fact that, okay, now we understand the scene, but then how do we actually make it output XR content? So to do this, the first thing we did is when we captured data, we also captured the world mesh. So we got the 3D world, and then we also kept track of the camera pose at which each of these images or audio data points are being collected. So basically each image is kind of marked or tagged by the pose. Now we then send this over to the server does its processing, we get the response, and now on the headset, we have this reality decoder block where we do 3D projections. So we have these 2D coordinates we got from Ferret as a response, and then we take that 2D coordinate with the image and the camera pose at which the image was taken and use that to raycast into the mesh to get the 3D coordinates of where certain objects that we cared about are in the scene. And we use this idea to then be able to generate arrows that point or that are anchored to those objects in our space. And then we also generate text overlays so that you can give a text feedback to the user. So overall, the architecture that we built looks like we have the physical world, we have sensors on the headset that capture information, we capture the image and audio information and process that or encode that into a prompt that's well understood by LLMs today, send it to multiple parallel LLMs, and we get text responses, 2D coordinate responses, send this back to the headset, where we then use the fact that we have the mesh and the camera pose at which these coordinates were found, or coordinates were calculated from, and then project that into 3D using raycasting. And then now we can have an intelligent XaiR response. Just a little bit of numbers to help people kind of understand how long this takes. The end-to-end system takes about 4.2 seconds, where a good chunk of that comes from the large language models. About like almost most of it actually comes from large language models, and the rest of it really comes from just streaming images across. And this is a variable number because it really depends on a lot of different factors. Firstly, it depends on like the resolution of the image you're sending to your models. It also depends on your network quality, how long your responses are that you're getting back. And so this is a variable number, but in our setting, we kind of got about 4 seconds, and that gives you a ballpark estimation. The other thing that's kind of interesting to note here is that when we use GPT-4 Vision, which is not something we could host locally, and we were actually querying to the OpenAI servers, it takes like almost double the time than it takes Ferret, which is, yes, a smaller model, but also a model we ran locally. And so there is a lot of advantages to running models locally because it's way faster. And then there's a whole privacy storyline also to it. But querying it to GPT-4 was the majority of our time for our system. Okay, so from here, let me jump to the kind of application we built on top of this. So using this architecture, we actually were able to build a cognitive assistant, which we use for instruction-based tasks. So this is an assistant that can firstly generate instructions based on an expert performing a task. So it watches an expert and then kind of gives us a list of instructions that the expert performed. And then the second part, which is probably the one that uses the entire architecture, is actually assist a new user to perform these instructions successfully. So let me walk through what that looks like. So firstly, for instruction generation, let's say we have an expert. This expert is doing some task. Now here in this case, I'm using a multimeter, and we're capturing ecocentric information from the headset. We then segment this into chunks, and we capture frames. We could do video directly, but since GPT-4 Vision doesn't do video, we actually just captured it as frames. We then pass each of these sections or frames through a large language model that can give us a good summary of what's going on. So it's essentially logging the user's actions. Using these summaries and some more context, we're then able to generate a set of instructions for a person to follow along exactly what the expert has done. So just for this was a kind of an attempt at actually logging users' actions. That was the focus. And because we're looking at an instruction following assistant use case, we actually went the extra step of generating instructions. But in general, it's pretty good at understanding the user's actions. So from here, let me look at the more, I guess, in my opinion, the more interesting part, which is the actual instruction following assistant. So this is an assistant where you have a person, they'll tell you what the instruction is, it'll watch what you're doing, it'll give you feedback, it'll give you the arrows pointing at objects, and it also allows you to actually ask follow-up questions. So you could say, hey, assistant, how do I do this? And it'll tell you. So here's a little demo video. It is at 2x speed, where I'm doing this playing back the same task of using a multimeter. So as you can see here, there's a instruction which says hold the multimeter in your hand. It also gives you the current instruction state, which is essentially telling you whether you've done the instruction or not and kind of what has not happened. This freeze frame is like right before it captured the next one, so it didn't capture the hand being picked up yet. But yeah, so it gives you XaiR responses, text that you can kind of use to guide you through the task. I'm gonna keep going, and then it auto advances, so it realizes that okay, the person's done the task, so it had advanced to the next step, which is that take the red cable, connect it to the rightmost port of the multimeter, and you can see the arrows are pointing at the cable at the multimeter, and this kind of helps give more like better delivered instructions. And like I mentioned, you also stop and ask it a question, and it'll give you responses to that question. I can keep playing this, but it is on our website. It is on the you can search this up. So I will skip forward from here. Okay, so the biggest challenge then became, how do you actually evaluate such a system? What we did is we had a user study where we tried to benchmark using this LLM-based cognitive assistant to a human-based expert to the same task. And this was kind of the idea that normally the way you'd have someone train you up to do a task is to have a person standing there and kind of watching you and giving you feedback. And so we tried to compare this LLM-based assistant versus a human. So to do this, if you look back at our architecture, we actually created this human backend that gets the same kind of information that the LLM backend does. So it's kind of just like substituting it. And the response from it also is in the same format and same method that that the LLM backend provides. This is kind of what our dashboard looks like. It's a little hard to see, but here we were able to annotate on the image, so you can draw a circle, and that creates this red bounding box, which is what Ferret also does. Well, where it like creates a bounding box, and then we convert that into 3D. You can also type responses, and you can get the current instruction, like what instruction the user is currently doing, all of which is information that we provide to the LLM. So the user did perform two different types of tasks. One is these basic tasks, which are like using wooden building blocks of different colors and coming up with different structures. And then the other one is more advanced tasks, which in our case we picked was working with a humidifier, so setting it up and turning it on, and then also using a multimeter to measure resistance. Each user did two basic tasks, two advanced tasks, and each one of them had one that was run by the LLM-based assistant and one which was run by the human-based assistant, and they didn't know which one's which. And so, not very surprising from here that the LLMs are not as good as humans, which makes a lot of sense because LLMs are maybe 3 years old at this point. So, we're definitely very new. That said, what really surprised us was that LLMs were not actually as far from humans, especially at these cognitive assistant tasks, as we had expected, at least. So yeah, no surprise, LLMs not as accurate as humans. But that said, the LLM only made 3 out of 30 errors for the tests that we ran, where we considered an error being it gets stuck at a step for about 40 seconds, where it doesn't realize that things have the person has done the task, or if it just progresses to the next one without completing it. And this kind of stems from the idea of hallucination that LLMs are known to be pretty notorious for. The second thing was that LLMs significantly made more queries for each instruction. So let me kind of explain what queries and instructions are, just to be clear. An instruction is, so if we have our multimeter and the first instruction is pick up the multimeter, second one is plug in the red cable, plug in the black one. Each one of those are instructions. And then queries is the number of times you're actually asking the assistant to look at the image, look at the information, and give me a response or give me feedback. So number of times you kind of had to ask the LLM in this case. Its LLM did take much more queries for each instruction, which means it took a lot longer to recognize the user's actions. That said, the thing that was very interesting is if you actually look at the time each of these assistants took to respond to one query, the human took double the time that the LLM took. And this is something that was actually quite surprising, because if any of you have played with ChatGPT or Claude or Gemini or whichever one you prefer, one of the things you kind of notice is that it takes a few seconds to kind of give you a response. And sometimes that's something that stands out and sometimes gets annoying. But then if you factor in this whole idea that a human actually has to type out a response, has to draw an annotation, has to process this information, then it actually takes longer for a human to respond, because there's that like response time that's added in that LLMs don't really seem to have as much. The last thing is we use the NASA task load index, which is a way to evaluate workload, or how like frustrating, how difficult, how taxing it is to work with this system. And we noticed that for an LLM-based assistant, it's almost double, though neither of them are really that high, because this is out of 100. But from talking to people, we realized that this mostly stems from the idea that you need to make multiple queries per instruction. And so a lot of the times they have completed the task, but they're kind of waiting for the LLM to get it. While humans have this like sense of understanding, because we can understand intent. So if I see someone almost plug in the cable, like I see them in the trajectory, I will just assume it's happened. So the key takeaways from this is, if we could improve LLM accuracy, that bridges the majority of these gaps. It reduces the frustration that it takes to work with it. It will reduce the time it takes to actually go through the entire task, because we've seen that LLMs are actually much faster at much faster at responding than humans are. The other thing that's important to note is that the LLMs that we have today are not really trained for this physical world data. So right now they require much more attempts to recognize the physical world when compared to humans, because humans, this is what we've done all our lives. But if we were able to actually train these LLMs on physical world data and not just things scraped off the web, it will probably be much better at responding to these things. Okay, so we did this work, but what happens next? Where do we go from here? So everything I'm going to talk from here onwards is kind of work that I'm working on actively right now. So it is a work in progress, and I don't have all the answers or full results, but I still want to kind of share my vision. So let's go back to this sense, reason, act framework. For sensing, we're using egocentric information, mostly images, some audio being more speech than it is, like auditory information. But can we do more? Can we get more data? Can we learn more? And in this world of AI, where everything is about data, more data, can we throw more data at it and understand better things? Well, the second one is, okay, so for reasoning, we're currently using LLMs, and we recognize that LLMs actually need to be better built for physical world interactions, and not what, like, that'll definitely improve accuracy. That said, as a research institution, this is something I would leave up to the big tech of the world, who have the resources to actually go and train all these things. On the action side, right now we're pointing out objects in the scene, and we've seen that this is actually quite helpful for a lot of people. And it's especially more relevant when you start working with more complex machinery and you need to turn one specific lever, but there's 8 of them in front of you, so which one do you turn? If you can point that out, that definitely gets more helpful. But can we also bring more meaningful responses in AR? If I have to plug something into the wall, can I actually have an animation of a 3D model of a plug plugging into a wall? Like, is that more helpful? Or even just like arrows that kind of suggest that you go from plug to wall. So can it give me better information about what kind, like the AR response? And so I've been working on both the better action side and the better understanding, better sensing, sorry. So on the action side, what I've been working on is trying to generate context-aware AR. So I don't think this is a crazy idea for most people here, but why do we care about AR generation? Well, firstly, if anyone's used Blender or even Unity to generate AR, you'll know that it's quite painful to actually do this. There's a high barrier to entry. You can't really make quick prototypes unless you've been doing this for years. But also, the other thing about using AR objects, especially in applications, is that you have to have most of them pre-scripted. You have to have created this object beforehand and kind of created the layouting of all of it beforehand. And so can we actually adapt it to the scenario users are in? Based off of where the user is and what the user is seeing, can we actually generate different AR objects in real time? And so, yeah, that kind of brings us to these requirements where, firstly, we want to be able to generate AR content from semantics, which fits the idea of, I want to know where I am. I want to understand what I'm trying to do, and then be able to generate AR based off of that. I also want to be able to have interactive prototypes. So interactive can be interaction between the human and the prototype, which is always helpful. But also, on the other hand, just have multiple models in my scene be able to interact with each other in meaningful ways. And then we also want to be able to edit, manipulate the scene in real time, especially for a cognitive assistant kind of application, where based off of what the LLM outputs as its instruction, you want to be able to show a different thing in the scene. You want to be able to generate that AR in real time. So ideally, we want to go from AR to natural language. That's what this boils down to. So some text prompt, something in the middle, to AR in the scene. And so here I'm going to make a very quick aside to Arena, which is a platform that my lab has kind of generated it started about 3 years ago, I want to say, and they've been constantly maintaining, which is a spatial web, which is cross-platform, multi-user platform where you can generate virtual and AR content. And then really nice things, it has a lot of features. The really nice thing that I personally care about is, well, firstly, you can create XR content during runtime or like as it's running in real time. And the way this kind of works is there's a pops up bus where all the different users, the things that are providing information, so sensors, agents, remote users, local users, all of them can be subscribed to, and then they get constant stream of information of what is being generated in the spatial web. The second nice thing that makes it sweet for AR generation is that, or XR generation, is that all of this is done through JSON and Python language, which are two formats or languages that are extremely popular. And these large language models that we have today are very well trained in generating this kind of content. And so you don't actually have to worry about a very specific, TypeScript or whatever it is, a very specific definition. You don't have to worry about that because this is something that's quite generic. As a little side video of how, one of the things that we have, one of the things that we support is this digital twin of this, little toy car that we have, where we have a bunch of sensors in it, and you can see that this AR version of this digital twin, AR version of it, so the digital twin of it actually changes as you manipulate the physical object. And while this is really cool that you have digital twins, it also shows the idea that we're able to make changes to the model in real time. And for more information on Arena, because there's so many more features to it than what I've talked about, there's this website, and it's free to use, and it's pretty well maintained. Okay, so jumping back to our text to AR generation world, our goal is to be able to do this in Arena, which makes it really nice to generate that code for it. And so to do this, we need to do three main stuff. Well, firstly, we need to give it Arena documentation, because it needs to understand, kind of what the Arena code looks like, even though it's a JSON or a Python. We want to give it a list of 3D models that we have and provide a way to kind of search through models, especially with a lot more fidelity than just say, place a cube, place a lion or something like that, like something more specific to our use case. But more importantly, we also want to be able to feed the scene back in. So this, again, plays back into our scene understanding game of we need to understand what is in our scene physically and in our XR content to be able to better manipulate it. So this is a work in progress. This is a slide that kind of very, very briefly shows a couple of the initial things we've done, where if we have text that says, place a clock on the wall, it places a clock on the wall. We can do some animations of, kicking a soccer ball into, well, what it creates is a goal. We didn't have a model of a goal, so it just created a wall-like thing. We can do funky stuff like make a man out of cubes, and that looks generically like a man. But basically, it's still work in progress, but we're able to actually generate visuals of different objects that kind of interact with each other and make sense with orientation, scale, and create these composite AR structures using just text. So some of the killer use cases that I think that this fits, well, the first one is this idea of manuals of the future, where we can take the manuals that we have today, which are like this 2D information or text that we have, and then add in user context. And with this combined, we're actually able to generate these AR-based instruction manuals that can be context aware, to the sense that, say you're working on a car and you are trying to change a tire, and it sees that you're changing a tire. It has its access to the manual where it can pull up the information about what changing a tire looks like. And then it can generate these instructions based off of what you're actively doing to kind of help you through that process. And then that's like changing a tire is probably a more simpler use case. This can go as far as as detailed and complicated as you can imagine. The other thing that I think this would fit really nicely is the idea of remote assist. So remote telepresence has kind of been a big thing in the last few years, where if you have a person who's working in like a factory or in a scene and they're not the expert and something goes wrong, then you call in a person to fly out, come there and help you fix what's happening because they are the experts. And that's obviously challenging, expensive, all of that. And so there's been a lot of work of, can the person who's there kind of scan their scene, be in like AR and send that stream back to a remote user who's an expert, and they can give you feedback on what to do because they're watching you actively do it. But can we go the extra step of, instead of them having to just tell you what to do, or maybe make some like annotations on your space, can they actually generate some models to help you better understand what to do? I'm sure this would be useful in 2D, but we're looking at, can we even bring this into 3D? And so those are some of the visions with this better action side that I'm actively pursuing. The other sense, which is definitely much more of an earlier work, is the better sensing side. So right now we're doing scene and action understanding based off of just egocentric sensors, more specifically a headset and just camera and audio. And while that gets a good sense of what the user is doing and what the user can see, it's still limited on the bigger picture of your space. And also it's limited by the field of view of where you're looking. So can we go the extra step of adding more sensors and more modalities? So could I have other cameras in my scene? So static sensors that are kind of looking at the entire space and not just what I'm looking at. And then could I have wearables? So could I have a watch? And say I have a task to like turn a lever a certain way. My visual part can see that I'm turning it, but then if it needs to be more fine-grained or there needs to be some kind of a click, can I have like an IMU or something in my watch that can actually see that? And there's a lot of work with wearable-based gesture recognition, activity recognition. And so basically, can we take all these different sensors and be able to get a better sense of what is happening in the user's world? And then why stop there? So most of us, especially when we work in look at bigger workspaces, we have a whole bunch of machinery, and the machinery tend to be the ones that are actually the hardest and most challenging to work with. So that's when you want an assistant. And most of these things are connected to the internet. So can we actually read information from them directly? So if I'm manipulating a machine, you can see what I'm doing. And then if you can get information about the state of the machine to kind of verify that what I did led to the right change in the machine, then you have a much better set of information to look at to kind of help you walk through a task. So can we do that? And then the other thing is, well, if each person is wearing a bunch of sensors, then each person kind of sort of becomes a sensor of their own. And so we can have people as sensors, we can have machines as sensors. And with all of this, can we now build up a much better world of what is happening in our space and use this for reasoning and responses? And so in conclusion, let's go back to the sense, reason, act that we had. We built XaiR, which was a platform that actually helps tie all of these three individual senses, individual ideas together to be able to put them in one pipeline, and then evaluated this cognitive assistant on that. We're now working at improving scene understanding by using more data and different modalities to get to better information. And we're also looking at improving the AR assistance by generating more meaningful responses. Yeah, and with that comes to the end of my presentation. I'm happy to take any questions. I'm also always looking to collaborate and learn a lot about what people are doing. So feel free to reach out to me, and I'd love to chat.
Fabulous. Thank you, Sruti. That was just really, really good. I thought it moved along at lightning speed, and it was very clear what you're talking about. You've given this talk quite a few times, and I first saw it at ISMAR. And congratulations on the best paper. I think it's best student paper, but congratulations. It was it was noteworthy. So today is even better because you weren't just talking about what you've completed and finished, but you responded to my request, which is, what are you doing now? And where is this all headed? That's really important. It's important for us all to know. So let me ask a couple of questions from the audience, and then I have some too. I thought one of the questions that somebody asked that you didn't share today, which is what happens in the system you already have in the XaiR if the user just makes a mistake or goes off course and starts doing something else. What does the current system do? Does it panic or what?
So yeah, that's a great question. So right now, what it does is it just keeps giving you feedback of whether you've done something or not. So if it notices that you're doing something that's wrong, or you just kind of abandon the task, then it'll be like, oh, I don't see the multimeter in the scene. I don't see what you're doing.
It doesn't add any more information because it doesn't have the prompt.
Exactly. So that's what it doesn't do. The nice thing that we have is that you can still talk to it. So if I say like, hey, assistant, I'm now doing this new thing, respond to the specific question, it does that. And we can use that voice to eventually change, like ask it to stop dealing with the instructions. But right now it's kind of set into like instruction mode. So it'll answer your specific question and then jump back into, let me, try to walk you through these instructions.
Okay, here's a great answer. And I'm sure you're thinking about that's part of the response, segment of the work. So looking at the sensing and part of it, you described that you had more than one LLM that you worked with. When you have more than multiple LLMs, how does the system give more priority to one or the other? How do you decide, or is it an algorithm? What's the weight in object detection or in generating a response?
So that's a great question. And this is actually so in this specific system that we ended up with, we ended up using 2 LLMs where each one kind of served a different role. So we had, for all the text responses and the reasoning responses, we had the GPT-4 give us that response. And then we had Ferret exclusively only give us like the object detection and coordinates.
They were assigned different roles. They weren't competing for the same role.
That said, what we did initially, we did in the intermediate space, we did explore this idea of, LLMs do hallucinate. They don't always get the answer right. So can we make this more robust by having multiple LLMs try and answer the same question? And then we kind of do a majority vote to be able to pick the best answer. What we realized was that I think that's still a good strategy, and there's a bunch of problems to solve there. We just never got to solving the entire problem because we figured it's a whole, rabbit hole of its own. But one of the things that we noticed was that it's also very hard to compare different responses. And this is the same problem we had with evaluation too, where it's not an objective answer. You can tell that task is done, not done, that's binary. But when you're giving feedback, it's no longer binary. And so how do you compare responses from different LLMs that are textual responses? And the answer that that the research community is kind of sort of landing on is use another LLM, which doesn't seem like the most robust way to do this, but that's kind of what people are landing on. And so majority vote sounds like a great way to do it, but it's really hard to quantize what majority vote is.
Mm-hmm. Good. So another question from the audience is, so you are inputting into the LLM some data objects, images, text, so forth. And all these are in different formats. The text is in text format, images are JPEGs, I guess.
Mm-hmm.
So can you list for us what content formats you have used, and what do you ask the LLM to give you back in terms of a content format? This is a question about interoperability, because you want to have any client, any user display be able to interact with the back end without having to customize. So what are the content formats?
That's a great question. And the answer is we're using text as input as well as images, but the images are all converted to bytes because that's what these large language models use. So you have to convert them all to bytes. So you could have a PNG, you could have a JPEG, you could have whatever. It just has to go into bytes. That's the input that we take, and then the output is just text. So the text there, we basically get text responses of like words, which is what you want to like print out, and then we have these 2D coordinates, and we're able to just parse that out from the text that we get. Yeah, and just for
lightweight.
Yeah. So I guess the biggest challenge in like replicating our code is that the actual server is like quite replicable. As long as you can drop in images, you could physically like have it in your store and throw it in, and that's easy to do. But when you're working with a headset, especially if you work with a headset, the biggest complication is most headsets don't let you get that data out. If you can stream camera, that's probably the easiest one, but getting the 3D content is even harder. So you like sometimes working with a phone is probably the easiest way to try and get that kind of data.
Okay. Now the question, I think people who are not researchers, but who are listening today and want to put this into practice in their maybe in their test beds, or in some kind of a constrained environment right away, because they want to take it into production. How far do you think we are between the research that you're doing, the prototypes that you're building, and commercialization? We know, the trough of this is just it's a gap, right? And a lot of people have to put it through. I like what you had, the figure where you said, we're not going to touch that because it costs too much. And you just had the logos of Apple, Microsoft, Google, and so forth. But have you seen any commercial implementations that come close to what you've done? Or, that people are knocking on your door saying, hey, we like what you're doing, come work for us, or can we build using your code? So tell us about this journey going to commercialization.
That's a good question. I know we talked a little bit right before this. So the very short answer to is there a commercial system for this is no. There's different things that kind of do different formats of it. So if you have looked at what Google's Project Astra, which is still their research prototype, but still, I guess, a much more closer to production level one, they do, you can like take your phone around the room and kind of scan images and ask it about, what am I looking at? If you've seen
kind of the Google Lens extension of Google Lens, like it translates and things.
Mm-hmm. Yeah, and then if the Meta Ray-Bans, they just do like image-based responses, they don't do like XR responses, but they do image-based responses. And then PTC has their like Vuforia check step, I think it's called, which also it doesn't do like LLMs per se, at least not that I know of, but it does look at the images to kind of know if you've done a task, and like advance between steps. So I think there's different flavors of commercial things that exist that do like silos of this. I've not seen something that goes end to end from like sensing to response. That said, a good chunk of our work was to kind of explore what this like end to end would look like and where it stands today. And it's definitely like there's promise. That's kind of the conclusion of this, that it's definitely promising, but there are gaps. And the gaps are like multifold. So like it's definitely you can't guarantee accuracy. You can say that generally it's quite accurate, but you can never guarantee that it's going to be 100% accurate. So that's definitely a flaw.
I think one of the things that people are asking in the chat too is around the complexity of the task, right? A simple task versus a hard task versus a 27 steps task.
That's a great question. And actually we have a figure about this in the paper also, where we basically look at scene understanding between like different levels of complexity of tasks. So you have stuff like just setting a table, placing your plate, your fork, your knife in the right places, all the way to trying to do soldering, which like in my world was like a pretty complicated task. And you can see that like the understanding of it definitely declines as you go to the harder tasks. That said, one of the things that we're actually actively exploring right now is using the idea of RAG, which is retrieval augmented generation, which firstly helps with hallucinations a good chunk, but also like we're able to throw in images of what things should look like. We're able to give a lot more it's kind of like getting as close to training it without actually having to train it, and give it more information about what these like tasks should be to help it better understand. And it improves it drastically. I won't say it's perfect. I don't think it's perfect yet. I think there's a long way
But
that
even the tuning that you're doing, it with the RAG process, it generates additional information, and one person asked, how do you protect that knowledge? I mean, like maybe you've been feeding these extra background or context information so that the LLM is more reliable, but that gives you this competitive, one particular instance of the LLM, a competitive advantage. And so then people will want to pay, maybe they want the free model or they want the trained model, or can certainly figure out that there would be some IPR issues or at least some business opportunities.
Yeah, no, definitely. And I think that's where, well, I don't know if it's a perfect solution, but that's where like running local LLMs kicks in, because if you have it on your own server, you're not actually giving out your data to
Exactly.
OpenAI or whatever. That said, the open source models are not as good. We also did a evaluation of like GPT-4 versus Lava, which was like the video model that was probably state of the art at the time when we did this about 6 odd months ago. And you can see there's a drastic difference. Now Llama 3 came out, which is like 480 billion or 480 million parameters, which is, 40 billion, sorry. Yeah, which is, much closer to what GPT is, but GPT is still in the trillions. So we're not there yet, but that's probably much better. But yeah, when we did it with like Lava, which was still much smaller, you can definitely see that the quality of results much worse.
Yeah, but on the other hand, like you said, if it's running locally and you train it to your environment, your tasks, your people, and recognizing those, then you're not trying to digest the whole world. So this could be pros and cons. Certainly, there remains some great research questions. Okay.
And the other reason why we're actually looking at improving sensing is also from the idea that if I can give it a more like undeniable proof of something happening, then it's better able to reason over that, and it doesn't have to actually figure out whether something's happening or not. And so like it's really hard, like you can't give undeniable proof. I think then we wouldn't need the LLM. But like the more streams that point to the same idea, if we're able to provide that, will it be able to give us a better response? And that's kind of what we're also looking at.
Yeah, have you thought, I mean, it's not text, but have you thought of a way to, like, again, in the sensing topic that you brought up, following hands, how could hand gestures be inputs to the LLM as a part of the query?
That's a great question. I guess we haven't explored it for that sense yet. I don't see I think that's actually a great way to do it. The other thing we've been looking at is gaze. Like also like, can we visually if you look at we've been doing gaze for the idea of like, if you're looking at a certain space, that's probably your area of attention. So can we only provide images of that area? And can that better like improve, like just like limit the additional data you're providing an LLM to focus it. I'm sure hands have a couple different ideas. Like one is like, you know where your hands are going to help you better see what you're doing. So, if you're like supposed to touch a button and your hand goes to the button, I feel like that's another way to know if you've touched it. But also maybe like there's an idea between, okay, wherever your hands are is probably where the main action is happening. So maybe we could do some segmentation there. Yeah, I'm just brainstorming here, but I think that would definitely be an interesting modality to keep track of what people are doing.
Yeah. For tracking their performance, but also anticipating what they're going to want to do now or next. Yeah, that's great. Have you done any measurements? Because I know that's what you really want to do, is do metrics about energy consumption, or have you detected that when, like you did a comparison of using the LLM versus the human? So was there any difference in performance or energy consumption? How could that be a factor?
By energy, you're talking about more from like the headset power side, or are we
Yes, that's what I'm thinking.
Mhm.
Yeah, I mean, I'm not going to talk about data centers because I think that's a much bigger question than we have time for.
That's a great question. So the headset, well, from our user study, the headset did nothing different.
Yeah,
there was
exactly.
like zero change. So there's nothing that really changed. I mean, I guess like the change would be that because using an LLM and it's not as accurate, it runs for longer. But all of our tests have been like in the few minutes number, so I don't know if that really changes much. I think running an LLM on the headset would definitely take a lot of power out of you. And so that would be bad, but we're trying to steer away from that because it's
right.
I guess like we've all kind of seen that the bulkier your headsets get, the more people don't want to use it. And so steering away from that seems like a more practical use case if you're using it in AR.
Absolutely. Great answers, great discussion. Thank you so much for taking the time to prepare and to share with us your knowledge. Good luck. We'll be following you. We're going to be very interested in what you do next, and all the people in the lab. I mean, this is, as you know, when I came up to you, there was somebody said, "Oh, I've spoken at the area before," or that your advisor had presented before. So it's great to see such a fantastic lab that's focused on the kinds of questions that area audiences are interested in. So congratulations, and keep going.
Yeah, thank you so much. Thank you for this, and yeah, thank you for everything.
All right, bye now.